My name is Alison, and I'd like to introduce you to the salt farmers of the Little Rann of Kutch. The Rann of Kutch is a seasonal salt marsh that lies in the Thar Desert in Gujarat, India. For approximately 8 months of the year, the 5,000 square kilometres is inhabited by salt miners and their families. Having lived here for centuries, they work here now illegally as the government has refused to renew their leases. Even though they produce a vast amount of India's salt, the Forestry Department believe they threaten an endangered wild ass by farming in this area. The salt farmers toil on regardless of this problem, under the harshest conditions. Living in temporary shacks beside their salt pans, they work in blistering heat with no guarantee of a profitable season ahead. Now, we were fortunate enough to visit numerous salt farms and spend time in the area in the Little Rann of Kutch, which helped us to understand the process of reducing salt under traditional methods and the problems that they faced. In brief, at the end of the monsoon season, when flooding subsides, the farmers begin digging by hand wells that access brine water. These wells are anywhere between 20 and 60 feet deep and are labour intensive. The brine is then pumped into shallow pans where evaporation occurs, producing salt. Now, to further our research, we met with Soji Bai and his family, a master trainer for Siwa. While discussing the problems that salt farmers encountered, he spoke of the 4 to 6 lives lost annually in the wells. He described the possibility of encountering a gas, either while digging or re-accessing an established well, that made it impossible to breathe and often took lives. He claimed no knowledge of what the gas was, and when asked what other problems he encountered, he expressed a desire for a pulley system that would assist in the digging of the wells to reduce labour. Our team then discussed 2 ideas: a way to extract gas from both closed and open wells to make a safer working environment, and also a portable mechanical jib system to aid dirt removal. We discussed a number of points, such as how might we identify an unknown gas that can be deadly when encountered, how might we remove a harmful gas from both closed and open wells so that a safer working environment is created, reducing loss of life. We also looked at how might we create something that would assist in the removal of dirt from wells so that labour and costs may be reduced, making salt farming more profitable. We hope to combine the 2 design ideas by attaching a simple extraction system to a jib pulley unit, but eventually we moved away from this and separated the projects. We felt the farmers should use the extraction fan continually, but only needed the jib system in the initial digging of the wells. We also took into account cultural considerations. First and foremost, we acknowledged that they had very, very strong family ties. We felt a project that may prevent loss of family members was actually of utmost importance. Focused on the gas extraction project, we considered how might we extract gas from wells to make a safer working environment and reduce the death toll of the salt farmers. Henry will now discuss further research for our design proposal.
Thanks, Alison. So, our gas extraction system is a simple way of removing harmful gases from the wells of the salt farmers and releasing it to a safer, more open environment. Through communications with the salt farmers and researching the characteristics of common underground gases, CO2 is suspected to be the gas that the farmers are inhaling. We cannot confirm this, however, as there have been no formal investigations into the gas or gases located inside the well. We suspect this because nearly 30% of naturally occurring carbon dioxide production is due to soil respiration and decomposition. We also considered other gases which are considered common gases found inside mines. Carbon monoxide was discussed but eliminated as it is a flammable gas, and the gas we are dealing with is oxygen depleting and therefore not flammable. Also, when carbon monoxide is found in mines, it is due to explosions and the use of internal combustion engines within confined spaces. Another deadly gas we considered was hydrogen sulfide. This gas was also eliminated from our discussions, as this gas is normally described as smelling of rotten eggs, and when asking the master trainers who had experienced the gas if it had a scent, they all said no. The master trainers are experienced ex-salt farmers who are employed by the Self-Employed Women's Association, SEWA, to train the salt farmers and assist in the implementation of new technology. The master trainers are the direct link between the salt farmers and SEWA. SEWA are the trade union run by women who are fighting for the rights of the salt farmers during a time when the government are more concerned about supplying a sanctuary for the rare breed of donkey known as the wild ass. Sewa have convinced the government that the people out using this land have no other form of income and therefore have been allowed to stay on the land. The relationship between the government and the salt farmers is a further reason as to why there have been no investigations in the type of gas in the wells. As the farmers are allowed to be on this land for the foreseeable future, the gas extraction system, or something similar, is most certainly required to protect the farmers. We suggest that this product, which will be further discussed by Dion later, should be tested by trialling commercially available air pumps with the assistance of salt farmers and master trainers. This is because these people are the ones that live there and they will know better than anyone else what they will use and what they will toss aside when it gets in the way. Once a viable air pump has been decided upon, the implementation process should be similar to the way that Sewa introduced their solar pumps to the farmers. This was done by beginning with 5 solar panels and pumps and allowing other salt farmers to see them in use and were gradually distributed across the desert. The solar panel project is an initiative set up by Sewa to reduce the diesel use in the salt farms. This was done by introducing solar panels and pumps to all salt farmers who were Sewa members. The farmers took out a loan with Sewa and had to pay back the amount of money that they were saving on diesel. This meant that the salt farmers were earning the same amount of money as before and were not increasing their cost of production. We suggest that our product be added on to the solar panel project so that farmers can continue to pay in instalments like they are currently doing. This small cost is a step towards eliminating dangers and reducing the number of deaths on the salt farms. I'll now hand over to Dion, who will further discuss the detail of our design and talk about our prototype.
Thanks, Henry. So, as Alison and Henry have now both mentioned, the design we're proposing is for a simple but innovative ventilation system to assist in maintaining a safe working environment for the salt farmers whenever they need to work inside their well. Some early design considerations were made after some broad initial research into what commercially available products are already on the market for confined space ventilation. While researching these solutions, we discovered many would likely be unfit for purpose due to their temporary nature of design. The light-duty PVC ventilation trunking being the most obvious suspected point of failure, being out in the harsh environment of the desert, exposed to direct sunlight, mud, dirt, dust and brine water for, as Alison mentioned, approximately 8 months of the year. Additionally, the cost for most of these systems is fairly high, so we wanted to see if we could come up with a design that could be put together from easily obtained low-cost parts that are already used or at least readily accessible through the existing suppliers to the salt farming industry, and ultimately end up with a solution that's going to be more economically viable than these off-the-shelf kits that are commercially available elsewhere. One of the more important design considerations that Henry, Alison and myself had to make was the way in which we would displace the gas that builds up in the wells. We concluded that the safest way would be to extract the harmful gas from the well rather than force good air down into the hole, as this would likely force that gas outward, uncontrolled, increasing the likelihood of exposure to persons standing around the well at ground level. The design our team came up with is assembled out of just a few easily accessed products, namely some low-cost PVC pipe with a screw-on end cap, which the salt farmers already have access to and use in the construction of their wells, that we're going to be using as an intake pipe with some holes drilled in it to allow airflow, but limit the amount of dirt and debris that can be ingested into the system. Some low-cost suction hose, which again the farmers already use as part of their solar pump system that Henry mentioned, but will probably require some larger diameter hose than what they currently use for pumping brine water, which should still be easily accessible through their existing supplier network. An inline duct fan, of which there's many options available that could be sourced and tested that are suitably sized electrically to allow the connection to the existing solar pump system, with many of these fans priced well, coming in at around the US $30 mark. An exhaust pipe system, which several design ideas already exist, and would suggest that the most appropriate would be selected during testing. The design we've chosen for our prototype is exhausting gas low to the ground, as that gas that we suspect to be carbon dioxide has already been identified by the salt farmers as being heavier than air. So we've decided that releasing it low away from persons should be an effective means of safely limiting any human exposure to that gas. And finally, some various fittings and hardware that'll be required to assemble the components into the completed system that should cost no more than $10 per unit, thus allowing our entire design to be delivered at a fairly conservative estimate of below $60 per unit, including an allowance for the cost of local labour to assemble it. One of the features of this design is the relative ease in which its capacity can be varied if required by simply purchasing different size components, although we think selecting a one-size-covers-all design would be the ultimate goal and would have to be decided upon after some testing in the field. In order to move on to our prototype, some initial rough calculations were made based on the information we had obtained from the salt farmers that we spoke to out in the field, mainly the volume of their wells, along with the data that was available for the 2 inline duct fans we had access to. Unfortunately, we were unable to purchase only a small quantity of the proposed 100mm PVC suction hose locally, so shown here is the alternative that we sourced, consisting of a combination of some black ag pipe for the connection between the intake pipe and fan, along with some white flexible internal PVC ducting for the connection between the fan and the exhaust pipe. And so while I leave you with some further footage of our prototype design in action, I'd like to pass you back to Alison to wrap up our presentation.
Thanks, Dion. As you can see, this video of a simulation demonstrates a fully functioning prototype. By replacing our choice of hose and pipe to PVC suction hose would further enhance the effectiveness of the design. We recognise at this stage we have no proof of what the gas is and are making informed assumptions of the volume and concentration of the gas. Identifying the gas by testing it in the field is paramount and where you would begin. We also understand at present we have no system in place to check that the dangerous gas has been eliminated by our design and a safe working environment created. As this is only the initial prototype, a number of designs would need to be tested in the field to ensure they are fit for purpose and would endure the test of time. Thank you.